Thank you for attending this seminar. I'm Abouzar, and I will talk about CO2-EOR and storage and some economic and environmental aspects of this process. And we use a case study from San Andreas Formation in Seminole Field in West Texas, Permian Basin. And I should acknowledge collaboration from Dr. Larry Lake and Lorena Moscardelli. So here is the content. I start with overall picture of CO2-EOR research at BEG, then CO2-EOR in the United States and Permian Basin. After that, I will talk about environmental assessment of CO2-EOR projects. Then a brief overview of 45Q tax credit in the United States for storage processes. Then I will come up with some questions and I try to answer those questions. The presentation actually has two parts. In part one, I will talk about CO2-EOR, and in part B, I will go further and I will talk about integrated CO2-EOR and post-EOR dedicated CO2 storage. And finally, conclusions. Bureau has a long history on CO2-EOR research. Up to now, around 33 journal publications, specifically on engineering or petroleum engineering aspect of CO2-EOR. And this is a number of journal publications per year. And these are some examples of these great research papers. And we continue those research. This figure shows overall, actually overview of CO2-EOR in the US. CO2 is sourced from natural reservoirs or from anthropogenic sources. Natural reservoirs are depicted by blue circles here, and pink squares represent industrial sources for CO2. Also, you can see the pipelines. Currently, there are around 140 active CO2-EOR projects in the US, and oil production from these projects is around 250,000 barrels of oil per day. So there are around 17 sources. 5 are natural, 12 are from anthropogenic sources. And these in general provide around 1.9 billion cubic feet of CO2 per day, which most of it comes from natural reservoirs. So industrial sources are greater in number, but they just contribute a small portion of the total supply. And this is oil production versus time since 1986. The peak production was around 300,000 barrels per day, and current production is around 250,000 barrels per day. And Permian is contributing to 66% of this production, which is significant. And this is CO2-EOR in Permian Basin, West Texas. There are 72 projects in West Texas, and these projects use CO2 from 4 natural reservoirs and 2 major industrial sources. CO2 supply is around 1.2 billion cubic feet per day. And again, most of it coming from natural reservoirs. And the question is this: does the source of CO2 matter? CO2 we use from natural reservoirs or from anthropogenic sources? When it comes to oil displacement physics, there is no difference. CO2 is CO2. The main difference is in environmental impact and their economic performance. Consider this diagram. This is when CO2 is coming from natural reservoirs. As no CO2 is separated from atmosphere, therefore there is uh, no mitigation of climate change. And even during injection and production processes in midstream segment, usually around 5 to 10% of purchased CO2 is flared or vented. So this is kind of even harmful to environment in terms of CO2 emissions. And this diagram on the right is when CO2 is coming from industrial sources, or it comes from air, direct air capture, or DAC. As CO2 is separated from atmosphere, then injected and accumulated underground, then there is help to mitigating climate change. So this is beneficial to environment. And from economic performance, usually the cost of CO2 purchase from natural reservoirs is less than $20 per ton of purchased CO2. And when we, in contrast, when we purchase CO2 from anthropogenic sources, the cost is greater than $40 per ton. And this comes with significant capex, and also greater OPEX compared to when we use a natural CO2, because here we have to pay for monitoring and some regulatory stuff that we should do. So these two sources differ in terms of environmental impact and economic performance. Let's talk about assessing environmental impact when we use anthropogenic CO2. This figure shows a life cycle of this process. We have upstream section. This is where we separate CO2 from atmosphere. Capture process is usually energy intensive, so there is some level of CO2 emission during capturing. So we call this emission as E sub U, or emission coming from upstream segment. And in the midstream or gate-to-gate operations, this is where we inject CO2, then CO2 displaces oil, CO2 is brought to the surface, purified, recycled, and re-injected. All these compression, lifting, handling, and separation activities, they need energy. And this is equivalent to emissions, CO2 emissions, greenhouse gas emissions. So we have another component of emissions here. And in the final segment, which is downstream, this is where the produced oil is burned. And usually 1 barrel of oil produces around 400 kilogram of CO2 equivalent upon combustion. So we have these 3 emissions: upstream, midstream, and downstream. And we have one component in midstream. This is where CO2 is stored. So basically, we consider this storage, we consider emissions, and then this is a material balance. Then we look at the overall net. Is net negative or it is net positive? One important parameter which is used in financial calculations for allocating 45Q tax credit is net CO2 storage. This is defined as the CO2 stored in the reservoir minus the upstream and midstream emissions. There is another parameter called net CO2 emissions. This is actually a true indicator of environmental impact. This is all upstream, midstream, and downstream emissions minus the CO2 that is stored in the reservoir. And during CO2-EOR, we have accumulation of CO2 underground. Some people call it loss, some people call it storage, some people call it sequestration. Uh, the choice actually depends on several factors. One is source of CO2. When CO2 is sourced from natural reservoirs, we usually call it CO2 loss in economic calculations because we pay to purchase CO2 and there is no financial benefit from underground accumulation. I mean, there is no tax credit because this CO2 is not coming from atmosphere. And here, operators try to minimize the CO2 that is lost in the formation to maximize their economic return. And in contrast, when CO2 comes from industrial sources or from air, this could be either CO2 loss or storage, depending on financial benefits. If financial benefit is lower than purchase cost, then we have kind of CO2 loss from economic standpoint. And if financial benefit exceeds the purchase cost, then we have kind of CO2 storage. Then there is a revenue, there is a profit in accumulating CO2 underground. And from environmental standpoint, here we have CO2 storage or we have CO2 sequestration, which is positive. Let's take a look at current and previous CO2-EOR projects. As I explained, most of the current CO2 supply comes from natural reservoirs. And that CO2 should be purchased. And actually, there is no incentive. There is no financial incentive for that one. As there is no financial incentive and we have to purchase the CO2, so we need to minimize utilization and loss of that CO2 in reservoir. So one technique is using WAG, in which slugs of water and CO2 are injected alternatingly. This technique actually minimizes utilization and accumulation of CO2 underground. This is what operators currently do. And this figure from one of the papers of Dr. Lake shows amount of CO2 that is accumulated in the reservoir per barrel of oil production. And this is for nearly all of the previous CO2-EOR projects in the US. Different projects have different patterns because they have different rock properties, different oil properties, and different operational settings. But on average, per barrel of oil production, around 5,000 standard cubic feet of CO2 is stored or is accumulated underground. So this amount is approximately around 250 kilogram of carbon dioxide. And when we burn 1 barrel of oil, it produces around 400 kilogram of CO2. So the net is 150 kilogram. We have 150 kilogram of net CO2 emissions per barrel of oil. And if this oil is recovered using other conventional techniques, then we have 400 kilogram of net CO2 emissions. So we can conclude that the oil produced by CO2-EOR is approximately 63% lower CO2. It has 63% lower CO2 emissions than other conventional oils. So it gives us oil and oil which is cleaner than other oils. And but one thing about this this number is that these projects have used natural reservoirs for supplying CO2. When extending this number to anthropogenic CO2-EOR, we should correct this number for those upstream and midstream emissions. Again, let's look at life cycle of this CO2-EOR. In upstream section, suppose we capture X amount of CO2. Usually around 20 to 50% of this CO2 is emitted in the process. And even in the midstream section, when we inject, produce fluids, if we store Y amount of CO2, around 5 to 10% of that one is emitted during this midstream operations. So when we account for these emissions, then this number actually goes down by around 25 to 60%. And this slide talks about financial incentives for anthropogenic CO2-EOR. There are two proposed techniques to implement incentives. One approach is applying direct tax credits like 45Q in the US. Companies capture and store CO2 and then they receive tax credit. Another approach is emissions penalty reduction. In this mechanism, emitters should pay penalty because of their emissions. And penalty can be avoided if emitters store CO2 underground. But the first one is the case in the US. And this current level of tax credits depends on source of CO2 captured from industrial sources or from air. And also it depends on application, whether EOR or dedicated storage. By dedicated storage, we mean pure CO2 storage in saline aquifers or in depleted reservoirs when there is no oil production. For EOR, when CO2 comes from industrial sources, credit is $60 per ton of net CO2 stored. And when we use this CO2 for dedicated storage, this credit goes to 85. And here, I should stress that this is dollar per ton of net CO2 stored. This is not per just CO2 stored. We calculate amount of CO2 that is stored in the reservoir, then we correct it for upstream and midstream emissions. So there are some questions in part 1 or part A of this presentation. What are the optimal operational strategies that enhance oil production and CO2 storage? Another question is that do incentives for carbon storage alter traditional field operations? Traditional field operations have used WAG. And the third question is that can incentives enhance the environmental performance of CO2-EOR projects beyond those conventional levels or not? And these findings benefit actually operators, government, and society. So the approach that we use for economic and environmental analysis has 3 components. We have a reservoir simulator, we have emissions calculator, and we have economic calculator. In reservoir simulator part, we calculate amounts of produced and injected fluids. In this cradle to grave emissions calculated, we consider the life cycle of this process by calculating upstream, gate to gate, and downstream emissions, and also amount of CO2 that is accumulated in the reservoir. We calculate 2 parameters. One is net CO2 stored, the other one is net CO2 emissions. This net CO2 stored is the one that I said is used for financial calculations when receiving tax credit. Then this net CO2 stored plus economic inputs like OPEX, CAPEX, oil properties, these things go to economic calculator, and we get NPV or net present value. And we use this parameter as an indicator for economic performance of project. And we calculate net CO2 emissions, and we use this as indicator for environmental performance of project. Then these 2 parameters are actually used for final economic environmental analysis. As I said, we used a case study from San Andreas Formation in Seminole Field. We use a sector model. This map shows location of Seminole Field. The map was created by Edna, and we simulated two operational strategies. One strategy is WAG, which is most widely used technique. The other one is continuous CO2 injection, which has been less used. We compared these two techniques. And by changing different operational settings, we generated 60 strategies. So, for example, what are these operational settings? CO2 injection rate, bottom hole pressure in production well, or well completion. Or when it comes to WAG, water CO2 injection volume ratio, or WAG ratio, or CO2 slug size, or bottom hole pressure in producer. And for emission model, in upstream, we use the average emission factor of 200 kilogram CO2 equivalent per ton of captured CO2. And in midstream section, we use the average 41 kilogram of CO2 equivalent per ton of compressed CO2. This figure shows oil production versus net CO2 storage. As I explained before, this net CO2 storage is calculated as the CO2 stored in the reservoir minus the upstream and midstream emissions. Here, WAG strategies are represented by blue circles, and continuous CO2 injection strategies are denoted by these orange squares. Generally, we can see that WAG gives a greater oil production, but lower net CO2 storage. And in contrast, continuous CO2 injection gives lower oil production, but greater net CO2 storage. And why this happens? Why WAG is associated with lower net CO2 storage? There are mainly two reasons. We can explain this by looking at amount of water that is produced during CO2-EOR operations, and also amount of CO2 injection. Here on this plot, we have net CO2 stored versus net water to oil production ratio. This is defined as net water produced after accounting for the injected water per barrel of oil produced. So we can use this as a proxy for volume of oil, volume of water produced. We can see that WAG has a lower water production. Lower water production means more water in reservoir, means less space for CO2 storage. In contrast, continuous CO2 injection has greater water production, means less water in reservoir, means more space for accumulation of CO2. Another reason behind this observation is that in WAG we inject less CO2. As I said, one of the functions for WAG is to minimize utilization of CO2. Utilization means use, means injection. So we inject less CO2, and therefore less CO2 is stored in the reservoir. And we also investigated a relationship between operational settings and oil production. Generally, oil production increases by increasing CO2 injection rate, and also lowering bottom hole pressure in producer leads to more oil production. Not always, it depends on case. Usually bottom hole pressure in producer is maintained at bottom hole pressure. In this case, bottom hole is maintained at minimum miscibility pressure, or MMP. In this case, MMP is 1400 psi. We reduced this pressure to 900 psi, but average reservoir pressure was still above MMP. So we have still miscibility, miscible displacement, and this increased oil production. Also, we found that completion has a significant impact on oil production. In these two completion settings, we observed the greatest levels of oil production. When completing both the injector and producer wells across their entire depth intervals, and also when one well is half completed in the upper interval and the other one is completed in the lower half. This also maximizes oil production. We also observed that increasing WAG ratio from 0.5 to 4 and increasing CO2 slug size, these enhanced oil production. And let's talk about environmental impact of these projects. Here we have net CO2 emission in billion SCF on y-axis. This is all upstream, midstream, downstream emissions minus the CO2 stored. And here we have time. When net CO2 emission is negative, it means we have carbon negative oil production. And when this parameter is positive, it means we have carbon positive oil. Here, CO2 WAG is represented by blue curves, continuous CO2 injection represented by orange curves. Initially, all EOR scenarios produce carbon negative oil. It means amount of CO2 that is stored in the reservoir exceeds all emissions in the life cycle system. But later, this net CO2 emission increases, and after some time, actually, all the strategies produce carbon positive oil. But here, the point is that CO2 WAG has always a greater amount of net CO2 emission. So CO2 WAG is less environmentally attractive compared to continuous CO2 injection. And also this figure shows a significant impact of project lifespan and operational setting on environmental impact of CO2-EOR. And here, let's take a look at NPV as indicator for economic performance. We have NPV on y-axis, and we have time on x-axis. We see that WAG is associated with a greater NPV. It means it is more economically attractive. Why this happens? Because in this case, we do not consider for carbon storage. Therefore, oil revenue derives the NPV, and CO2 accumulation is just a cost component. There is no credit, there is no revenue, and this is in agreement with historical field applications. Now let's put these two figures side by side, the one for environmental impact and the one for a net present value. So WAG has the greatest net CO2 emissions and greatest NPV. So there is kind of a trade-off. WAG is less environmentally attractive, but more economically attractive. And we can say that there is a misalignment between economic and environmental outcomes. How can we make alignment between environmental and economic goals? By introducing incentives to the system. These two figures show net present value versus oil production and net present value versus net CO2 stored. As there is no incentive here, oil revenue drives NPV. So the strategy that has the greatest amount of NPV produces the greatest amount of oil production. So oil production drives NPV. And here, this strategy comes with very low net CO2 storage because there is no revenue from storage. So, let's see how introduction of incentive changes the relationship between economic and environmental goals. When we introduce incentive to the system, those strategies that are associated with greater net CO2 storage, they benefit more from incentive. So we expect that continuous CO2 injection benefits more from this incentive introduced to the system. We find the break-even incentive that can equalize NPV of WAG and NPV of continuous CO2 injection. So if incentive goes below break-even value, then WAG maximizes NPV. And if incentive exceeds break-even value, then continuous CO2 injection maximizes NPV, which leads to alignment between those economic and environmental goals. So this figure shows NPV versus net CO2 emission under the scenario that there is a break-even incentive. In this case, a break-even incentive was $75 per ton. This is a break-even level that equalizes NPVs, right? So we have one strategy here depicted by this orange star. This belongs to continuous CO2 injection strategies. This has the highest NPV. We have another highest NPV within the WAG strategies. So these two have comparable NPVs, but different environmental impacts, different net CO2 emissions. So if operator uses this one, it's get most of economic profit, but very low net CO2 emissions. And if operator continues with WAG, it gives greatest level of net CO2 emissions. So it comes to the operator and what they choose. Here we have NPV versus oil production. For this scenario that there is a break-even incentive. If operator chooses continuous CO2 injection, I mean if operator prioritizes environmental impact and chooses continuous CO2 injection, then we have kind of reduction in oil production. It compromises oil recovery. And if operator chooses this WAG strategy, we have a still highest level of oil production. And the same for NPV versus net CO2 storage. These two have comparable NPVs, but different levels of net CO2 storage. Here, the main takeaway is that previously we had a trade-off between economic and environmental goals. Here, the type of trade-off changes. This time, we have trade-off between oil production and environmental impact. So when it comes to decision making, as I explained, operators have two choices. I believe operators will likely choose WAG because WAG has a lower CO2 requirement. And in cases where supply of CO2 is not sufficient, operators choose WAG to actually allocate the available CO2 to other projects. We have currently CO2 supply insufficiency in Permian Basin. So I believe operators will likely we likely continue with WAG. They do not change their traditional strategies. And if operators prioritize the environmental impact, then they may change to continuous CO2 injection. But this one gives a lower oil production, and we will have trade-off between oil production and environmental performance. And if incentive is significantly higher than break-even incentive, then operators will go for continuous CO2 injection, because this type of a strategy then maximizes both economic and environmental benefits. Here I have calculated the break-even incentive for different oil prices and CO2 purchase costs. Here on y-axis we have this break-even incentive. On x-axis we have oil price, and each curve shows one CO2 acquisition cost. This break-even incentive increases with oil price and also increases with CO2 acquisition cost. And this is the current 45Q in the US, $60 per ton. So what we see is that nearly all of the calculated break-even levels are greater than current 45Q tax credit. So so I believe the current 45Q is unlikely to change the traditional CO2-EOR strategies. By traditional strategy, I mean WAG. So no shift, toward continuous CO2 injection, unless government increases this level of incentive. And now let's go to part B. In part B, we talk about this dedicated CO2 storage. We usually put EOR as a tertiary recovery after primary recovery and secondary recovery. After tertiary recovery, there is still some room for dedicated CO2 storage. By dedicated, I mean when we close production wells, when we do not produce oil, and we just inject CO2. This dedicated CO2 storage is analogous to CO2 storage in deep saline aquifers, but with some distinctions. Here there are some advantages. In case of depleted reservoirs, we have availability of infrastructure, and also we have reservoirs that are well characterized, and we have lots of data. For example, we have injectivity data. By the way, there is really limited research on integrated CO2-EOR and post-EOR dedicated storage. This is why we performed this research in part B. So here are the questions. What is the optimal CO2-EOR strategy when transitioning to post-EOR storage? And can integrated CO2-EOR and post-EOR storage be optimized for greater overall value? And how to find optimal incentives for post-EOR dedicated storage? We used the same reservoir model. We simulated two strategies. One CO2 WAG for 10 years, followed by 3 years of post-EOR storage. The other one continuous CO2 injection for 10 years, followed by 3-year post-EOR storage. And we kept identical conditions across these strategies to have a fair comparison, to have an unbiased comparison. This figure shows CO2 storage for continuous CO2 injection, orange curve, and WAG, blue curves, for CO2-EOR phase and post-EOR phase. In EOR phase, we have more CO2 storage by continuous CO2 injection by around 41%. And this advantage in terms of more CO2 storage increases during post-EOR phase. So after these two phases, continuous CO2 injection gives 86% more CO2 storage. So there are two takeaways here. Post-EOR phase holds significant potential for CO2 storage, and post-EOR phase is more efficient if following continuous CO2 injection. There are two reasons why this happens. One reason is because of lower water saturation in continuous CO2 injection. At the end of continuous CO2 injection, this is a map of water saturation. Water saturation is really low, and this creates a significant space for CO2 storage. In contrast, in WAG, we have component of water injection, we have component of water production. So depending on balance between these two, we have either positive or negative net water produced. And generally, we have a really high water saturation at the end of WAG scenario. This lowers amount of CO2 that can be stored. Another reason is because of lower reservoir pressure in continuous CO2 injection. This causes, more CO2 we can store in reservoir. And both strategies approach to the same pressure. This is where we stop injecting. This is where reservoir pressure reaches some levels that we should not exceed. And this is about net CO2 emission or environmental impact. Initially, net CO2 emission is negative, then become positive, and during post-EOR, net CO2 emission goes down. Even here we can see in the case of continuous CO2 injection, this even goes to negative values. This means this post-EOR CO2 storage has a significant potential to lower emission intensity of produced oil during the EOR phase. And this is a NPV versus time for this integrated system of two phases when there is no incentive. As I explained, in EOR phase, when there is no incentive, WAG gives a greater NPV. During post-EOR phase, both NPVs decline because there is no incentive, there is no revenue. So operators are unlikely to transition to a storage phase. There is no revenue, and therefore we need these financial incentives for post-EOR phase. And again, let's put these two figures side by side, one for environmental impact, the other for economic value. We have a trade-off similar to the previous part A. We have misalignment between economic and environmental outcome, and the only way to make this alignment is using incentives. So we calculated break-even incentive. This is a break-even incentive in the post-EOR phase, in the second phase of project. And if incentive goes below break-even value, the strategy that uses WAG and then post-WAG injection, that one maximizes NPV. And when incentive is greater than break-even value, then the strategy involving continuous maximizes NPV. We calculated this break-even incentive for different oil prices, different CO2 purchase costs, and different EORs, different incentives in EOR phase. We did this for different CO2 prices. Here, I just show one of the figures. This is where CO2 acquisition cost is $40 per ton. Generally, amount of incentive in post-EOR phase decreases when we have increase in EOR incentive. Suppose that there is no incentive in EOR phase, then there is a significant need, a significant incentive required for the post-EOR phase. So we need some kind of incentive here in EOR phase to lower incentive in the second phase. And also this break-even incentive increases with oil price and with CO2 acquisition cost. So conclusions, WAG gives a greater oil recovery, but lower net CO2 storage. And without incentives, there is trade-off between economic and environmental goals. We need incentives to align these two goals. And also we found that current 45Q tax credit is unlikely to change the traditional WAG strategies. And we observed that the post-EOR phase holds a significant potential for CO2 storage and for reducing emission intensity of the earlier EOR phase. We published two papers from this research, one in International Journal of Greenhouse Gas Control. This is on the EOR part only, part A of this presentation. And this SP paper on integrated CO2-EOR and post-EOR phase. Here, because of limited time, I just presented a fraction of results. If you are interested, I refer you to these two papers where you can find more. Yeah, many thanks for your attention, and I'm happy to answer your questions.
Thank you very much. We're open for questions online as well. Sue?
So some your results disagree with some of the older papers, and I think I'm trying to figure out why. You know, so Vanessa Nunes did a study that was of two different reservoirs. She didn't do San Andreas, she did Sac Rock and Cranfield, where we had lots of data, and got very similar results about the virtues of WAG versus the virtues of a direct injection, continuous injection. I think you're missing maybe the distinction is that what Denbury told me about the upfront costs of the capex of bringing on WAG versus doing continuous injection. Denbury finds it effective to avoid the cost of water handling in a field that doesn't have water handling, whereas the West Texas fields have water handling because the EOR is coming on after water flood. But in some of the other fields, what they don't have good water drive, they haven't had a water flood phase, so that they don't have all the infrastructure to handle water. So the cost of water handling, both the infrastructure cost and the capex and maybe the opex, water handling, as we know, is quite a expensive activity. I wonder, that's one of the reasons. That Ramon Hill and she and the work they did not get very high midstream costs. I remember this vividly because I thought you were right. The midstream costs were going to be very important, but their numbers for the midstream, both losses, they had very small losses of CO2 in the midstream, and the major thing that was causing midstream emissions and cost was gas separation. When you're trying to get the condensate out, that's where you got the cost. So I wonder if you've got condensate mixed in there, and in the midstream, you know, the on in-field operation, you know, operational cost and CO2 emissions if you're including liquids. Also 45Q is agnostic to any kind of information you have about the life cycle, and it probably shouldn't be. It would be interesting to invert your results and think about why we as taxpayers would get better bang for our bucks if there was a life cycle element in our tax credit. Right now, you're taking the tax credit. Well, tax credits are your calculation is doing a life cycle, and our national incentive is not considering a life cycle. You know, you
It
just get a
is.
flat, it's not, it's a flat
It
fee.
is per net CO2 sort, and
No, but
we
it
do the
doesn't
same.
take off any of the upstream, any of the midstream, or any of the
Yeah,
downstream.
no
Just
yeah.
tons in the ground. It's
Yes.
just tons in the ground. It has no, and emitted from the project. You have to take off the tons, but it has no life cycle consideration.
Yes, yes.
So
Correct.
the issue, some of the issues in front of us is if we did life cycle, what would we do and how would we optimize benefit all the way around?
We have done this actually. The true environmental indicator, as I said, is a net CO2 emissions. So we should consider downstream segment as well, right? The amount of CO2 that is emitted from oil. And this is not considered in credit. So we actually proposed a technique to address actually your questions. I didn't present it today, but you can find it here. So we proposed that incentive be allocated based on environmental performance of different projects. Currently, different projects all use the same level of incentive, let's say $60 per ton. But some are cleaner, some are not, and this is not fair. We propose that here we propose efficiency-based tiered or multi-level carbon storage incentive to address that question. But I didn't present it today because of lack of time.
Do you stand by those high midstream emissions? Do you think those are better numbers than what Ramon Hill has? If so, would you tell him why he needs to change his numbers?
Excuse me?
The midstream emissions
Mhm.
cost, he did a bunch of calculations based on something or other, and we'd have to ask him what it was, but he got much lower
Yeah.
midstream emissions
For-
than you did.
Yeah, for we first of all we included all those upstream and midstream emissions in calculations. The point is that these emissions are case specific. For example, in EOR phase, we suppose that compressor increases injection pressure to 1,500 psi, right? So then we use emission intensity of Texas grid system to calculate amount of emission for compression. But if reservoir changes, if injection pressure changes, then all midstream emission calculations change accordingly, right? So this is a kind of case specific. Another thing is that when we compare WAG versus other strategies, for example, continuous CO2 injection, right? We should compare this under identical conditions. Otherwise, this comparison is not fair. In previous research, what I have found is that in most of them, the comparison is not fair. Some of them, for example, have shown that WAG gives lower oil production. And when you look at the paper, they have injected less CO2, or they have used a different completion. So it's very important to have identical conditions for the comparison. Yeah. Okay. Yeah, so
I'd like to see somebody working more on the poor scale physics.
Mhm.
You know, we're making these upscaled simplifications in the model, and they're three-phase flow, damn it, or four. So things are complicated. So I wonder if anybody's working on the poor scale, the underlying physics of the whole shebang, above my pay grade, but I'd like to see it sometime.
Yeah, interesting. One more point about that water availability. As I said, most of the previous EOR projects have used WAG because water was available. But there are some cases where continuous CO2 injection has been used, even in Permian. For example, when reservoir is tight, water injectivity is low, so operators prefer continuous CO2 injection. Or in the case that you mentioned, they have used continuous CO2 injection. So water availability is very important. Also, formation sensitivity to water is important. Sometimes it causes clay swelling, it causes formation damage. Also, injectivity is important. In this case, we assume that water is available, right? Water is available and injectivity is good and there is no clay swelling. So yes, we considered water lifting, water handling, water separation, CO2 recycling. We accounted for most of these operational or OPEX parameters.
ISO working group on conversion too. I don't see that reflected in your work. I'm not sure it's a very good study, but it was a lot of people put a lot of effort into conversion from a EOR operation into a and the main problem is whether you've got that space, that pressure space.
Yes.
And which would depend on a couple of things, water drive and what they were operating. You know, that study that Mehdi did which field was that, Mehdi, that we did anyway? It was operated above frac gradient, and so you couldn't, you know, what? That was Denver unit anyway. Yeah, it was operating above frac gradient basically, and would never have been permitted for storage anyway. And there probably wasn't any pressure space, but your field, the one you've done you left pressure space. You weren't operating at the highest possible pressure. Admissibility was attained, I guess, at lower pressure.
Exactly.
So that part of the equation depends on local specificity, whether there's pressure
exactly.
space and whether the water drive to continue injecting after you finish what?
Yes. Several factors
affect. Some of them were disposing of water to accommodate space too, which is in the Permian. Yeah, we want to do more water disposal because that'll make money fast. But anyway.
Thank you. The reason we use San Andreas in Seminole is that most of the EOR projects in the world have been done in US, and in US most of them in Permian, and in Permian most of them on San Andreas. So this is the reason actually we use this case study. But I fully agree that reservoir properties affect these things. Reservoir drive, fracture gradient, even completion types of well, horizontal, vertical, these things, even fractures, all these can affect the results. Yeah.
Julia?
Yeah, I want to talk about something else. I don't think you mentioned it for the tax credit. As far as I understand it, you have to do significant monitoring to make sure the CO2 stays in the ground.
Yes.
So that you're getting credit for what you've done. I wondered in the two different, the WAG versus continuous, whether the amount of CO2 getting out might be different, because in the second one, you're putting more in. I mean, do you know anything about that? And was the cost of doing the monitoring in the OPEX part?
Yeah, one assumption that I have seen in previous research works is that, this monitoring cost, it is dependent on several parameters like location, operator. Usually people assume that monitoring cost is around 10% of operational cost, right? This is one assumption. And in continuous CO2 injection, operational cost is higher. So more, more operational, more monitoring cost. Excuse me.
New thesis that Argenis Mayalo is finishing, saying the highest environmental risk is handling the brine. Said that if you're handling more brine, you probably should have more environmental risk and therefore higher. For example, he's working on insurance premiums, but he would put the insurance premium higher if you're handling more brine because it's more hazardous in terms of his calculations, which are incredibly complicated and could be argued with, but that's where he was.
Yeah, we actually received this comment previously from Mark Schuster. When we talk about environmental impact, there are several pillars. It can be CO2 emissions, it can be produced water handling, it can be seismicity, it can be different things. Here we focus on just net CO2 emissions. Yeah.
Any other questions?
Great presentation. My question is about continuous CO2 versus WAG. So considering that water is produced always with oil, if you decide for continuous CO2, to consider the cost of disposing of the
Yes.
produced water?
Yeah, we did. Yeah. We have all this lifting, handling, disposing. We have this cost in the model. But one general point, without doing any simulation, reservoir engineering principles say that in general, WAG gives greater oil recovery and therefore lower CO2 storage. It means less, environmentally beneficent. So this is general reservoir engineering principles. And here we use this quantitative analysis to quantify this advantages, this versus that. But in general, the results, follow the principles of reservoir engineering.
So, one last comment.
So when Vanessa left us, where we were talking about is comboing, how you combine the two. Partly, a reservoir is not just the oil, it's oil plus saline. So the intersection of the two could be very potent. If most of the infrastructure cost is the pipeline, is to get to and then the well, and then the monitoring to get to location. So if you did optimized EOR, which we all agree it involves keeping a front straight, avoiding early breakthrough. So using water to manage the CO2 very effectively. This is a positive. Everyone agrees. It doesn't seem to be much doubt, unless, as you say, there's a problem about the reservoir properties, but most cases. But then there's nothing to keep you from using other parts of the same complex. And then the water leg becomes a commercially attractive item. And so you could, instead of picking one or the other, you could optimize your completions to use both effectively, and it has to do, it intersects ROS, that using the lower part where oil concentration is lower, and maybe you don't have to make a lot of money on ROS, but if you're using it mostly for storage, I don't know, there's some interesting ideas about comboing the two to optimize both without sacrificing one to the other. It's fertile research territory, I think.
Yeah, thank you.